Thank you for coming. Wow, this is a lot of people. This is more interest than I get at my own company. That's not for the record. All right, let me just introduce what I do first. So we're Zopa. It's a world's first peer-to-peer lending platform where investors can lend directly to borrowers. So the way we do that is investors come to us with their money, and we split that into a large number of assets, which we call microloans. And then those microloans are used to fund loans for borrowers on the other side of the platform. Here are a few numbers to show that it's a business that works. We've been around for more than a decade, lent out more than £3 billion. But today I'll be focusing on that portfolio optimization part where we need to form essentially bags of assets for our investors such that they satisfy constraints, meaning that portfolios get a certain amount of return for a given amount of risk, and among many other things. I will show how to frame that problem as an integer programming problem. So yesterday, Gianluca spoke about how it's actually one of the more difficult optimization problems, and I'll discuss how we solved it on our platform and use the PyData stack to make it very, very fast. Conceptually, it has applications that are much broader than just portfolio optimization. You can apply these insights to capital budgeting, cutting stock, scheduling, and many other problems. So what unites them is that these optimization problems are combinatorial, and so are NP-hard, which in plain English means that they're intractable. They don't scale well, and if you just try to brute force them, you'll never get a solution. This is how you would formulate them mathematically. Don't be intimidated by the math. So all it says is that we need to assemble the most valuable portfolios for our investors such that they are affordable, i.e., well, the money that they gave us need to be spent. They need to be of a certain risk profile that satisfies their preferences, and they need to yield a certain amount of return, among other things. So the key constraint that makes this problem difficult is the last one, actually. This is an integer programming problem. You cannot use gradient descent, and in the worst case scenario, you'll just end up enumerating all possible cases, which in this case is complexity of 2 to the power m times n, where m is the number of investors and n the number of microloans. Formally, this is what is called a multidimensional knapsack problem. Yesterday, Gianluca, in one of the PyData sessions, showed that even with 1 million assets, he couldn't solve it on his laptop exactly. So, you know, if that doesn't convince you that this is not a trivial problem, there's a textbook just on the variations of this single problem. It's 300 pages, and it's full of dense proofs. So, you know, that's when you know your manager threw you an interesting problem. Luckily, in the ecosystem, we have third-party solvers written by companies like Google and C++ with Python bindings, usually very fast, very reliable, or you can go about it using genetic algorithms that would smartly explore the solution space. The problem with them is that especially the third-party solvers that we tried, is that they are very slow, even though they do something smarter than just brute force, what is called branch and bound. Still, because in the worst case, you're still enumerating every possible case, it can take days. This is how you would set it up. So very briefly, you essentially need to initialize a bunch of integer variables. You define the constraints. So the constraint number 1 is what I call the affordability constraint, right? So you just need to be within your budget. And the second one is the return constraint, which is you need to get a certain amount of return. And finally, the last one is the objective, which we simply tell the OR tools. This is a Google optimization, operations research tools to maximize. Unfortunately, at our scale, it won't work because it needs to solve essentially for a matrix of m by n, m investors, n microloans, and that's billions of variables. It can take days to do that. And in addition, when you design something more custom that is less abstracted from you, you can incorporate business priorities in an easier way. And that's the path we chose to design our own algorithm. Of course, because the problem is NP-hard, we couldn't do that exactly. So you need to simplify these kind of things. The key simplification is that we're not looking actually for the very, very best solution. We just need to find a feasibly good one that gets a certain amount of return, certain amount of risk, while exhausting a person's budget. The key insight from a technical point of view is that the knapsack problem has a greedy choice property, meaning that you can advance one step at a time. You simply have to iterate through assets, and for everyone, select the most appropriate buyer using some heuristics, and those heuristics are usually created using nuanced business knowledge. Because it's a single loop over assets, and for every asset you need to evaluate suitability of every investor. In the worst case scenario, complexity is only to the order of m times n, which is orders of magnitude faster than 2 to the power mn. This is the solution at, say, bird's eye view. We process investors that come to our platform in batches. They go into a common pool of these kind of microloans, assets, and then the portfolio optimization algorithm or the matching algorithm forms new portfolios. A brief note on how to design this kind of greedy algorithms. It's a very general problem-solving technique where you simply make the best choice at the current step without looking ahead. You are affected by what happened before, but you're not looking ahead. And in machine learning, an example of an algorithm that does exactly that is actually the ID3 algorithm to learn decision trees. At every node, you are splitting by the best variable without thinking of how it might affect you down the path. This can be a lot faster than enumerating all possible cases as might happen in dynamic programming or branch and bound. Key components that you would need to create or write yourself are the feasibility function, so filter for the appropriate candidate set, the investors that are actually eligible for this asset. A selection function based on heuristics. For every asset, you need to calculate some suitability and then assign to that investor. And a solution function that checks actually that all the constraints are satisfied, because some of you may know, so the greedy algorithm does not guarantee that the solution will be, well, not only does it not guarantee that it will be optimal, it does not guarantee that it will satisfy the constraints. So that's why you need to be wary about that. This is an illustration of how that algorithm works. So you have a bunch of assets in there, you trade one by one. So you're considering, let's say, this green ball. And you're thinking, okay, which investor do I give it to? The scoring function then calculates some score. The logic at a high level is basically, we know where we need to get you. We know where you are, and we hypothesize. So if I were to give you this asset, how much closer would you be to your target portfolio? So in this case, the second investor is the one for whom this asset would benefit the most. It would bring him or her closest to their target portfolio, and so the asset would therefore be assigned to them. As you can tell, this is very custom. You won't find libraries to just import and do this for you. So we wrote this completely from scratch. Our backend is very Pythonic, and in general, we love Python. So we didn't want to have components written in C or even Python. So we wanted to leverage the best that the PyData stack can offer and follow roughly this kind of workflow where we prototype in pandas. So first, you always need to optimize for research speed. When you don't know what the heuristic should be, you don't know what the algorithm looks like, And pandas usually is very good for that. It's very convenient for database connections, data manipulations. Group bys can be very painful in NumPy. So pandas is the way to go. Secondly, when then speed becomes crucial, the easy thing to do is to perform computation on NumPy arrays, parallelize where possible, and the last mile when the algorithm is performance critical, you can compile it using Numba, and I'll discuss those steps in detail. So the algorithm is ready. Now you know that okay, I need to make it fast, because when you move people's money around, a transaction failure is very costly, and we work in a very regulated industry, so these kind of components need to be robust. But before refactoring code, always profile. Even with intuition, sometimes you can be surprised actually when certain things are faster than others. So in Python, you either have the choice of largely CPython, which will profile every function in the module, or what I prefer personally, the line profiler extension to the IPython, where you simply need to load it, and you can profile every function call down the stack, and then every single line in the function will be profiled for you. So in this case, I'm profiling the function score asset, which is called inside allocate assets, and saving that function, saving the results in the file scoremcl.txt. And this is roughly how the output might look like. It would go line by line and show you how many times that function was called, how many seconds were spent there per hit, and percentage of time overall. So you will know where to focus your efforts, essentially, and which parts to leave alone and which parts to refactor. Here's another example of a profiling report. So you start writing pandas. You have a huge data frame of portfolios with all sorts of metrics, and you need to index them during iteration. That is very, very slow. So as you can see, going from pandas to NumPy purely for indexing can deliver 230x speed up. That is just massive for something that is a relatively small change to the code base. Let's delve a bit into why that is the case. So data frame is simply a wrapper around a NumPy array. On top of that array, it will provide you a label axis. So indexes for rows and column names for the other dimension. Indexes are essentially a big mapping. They are immutable. So knowing things like that can help you understand why certain operations should be avoided and why they are slow. So, for example, in a numerical algorithm that is iterative, you will be adding stuff appending stuff to an array. If you do that with a data frame, that will be very slow because the index is immutable, and every time you append, you're creating it from anew and copying everything again. Each data frame column is a pandas series with an underlying NumPy array. It allows pandas to store arrays of heterogeneous types, i.e. different columns can be of different types. But if within the same column you have different types, for example, strings and integers, it will revert back to Python object container type, which will prevent any type-specific optimization due to NumPy. Here's a slide from Jeffrey Tratner's talk, and also I think Jeff Reback, so both of them contribute to pandas. They've touched on this before, of how, for historical reasons, pandas stores data frames in memory. So it's not just one big data frame. Actually, it stores axes separately, so column names, indexes, and then blocks of data according to their type. So the orange block is just object. Then you have integers, booleans, floats, and so on. And when you append, you will be creating all of this from scratch again, copying and then adding that new row, rather than modifying in place for that memory slot. That will be very slow. The key takeaway is do not rely on pandas when speed is crucial. Avoid appending to the data frame, especially when your loop is over millions of items. Avoid applying a function with using the apply method to rows, because it will, behind the scenes, it's just a for loop that is indexing every single row. So, and as you saw, indexing in pandas is super, super slow. When you do need a data frame, for example, for the consumer of the algorithm at the end, or for some data manipulations inside the algorithm, or for some database connection and so on, create it once at the very end, outside the mathematical logic of the algorithm. If you must iterate, the best way to do that is through the iter-tuples method. It's a generator that will give you every row as a named tuple. And knowing how pandas actually works from what we just seen, you can reproduce the functionality in Numpy. So columns might be coming in different order, right? So it's not always the case that price will be first, then it will be an investor's capital. So that's why indexing by a string is so convenient. You don't need to worry about, okay, which one is the first, which one is the second. In NumPy, you won't have that luxury, but you can recreate that functionality by creating extra data structures that mimic what pandas axes give to you. So here you have an NumPy array with a bunch of data. Obviously, you don't have column names, but you can create a dictionary, or even better, a named tuple, where the string is mapped to a number. So price is mapped to 0, for example. And when you index a NumPy array with the second dimension to the dictionary's item, you will get exactly the column 0. I hope that makes sense. That way, you get rid of pandas while still having the functionality of the indexes and column names. And as I showed you earlier, also, that's what will allow you to work to move seamlessly between from pandas to Numba and just-in-time compilation. Next is parallelization. So, for example, when in our algorithm, when we score investors for the asset, that is done independently. One investor suitability for that asset is independent of another. That means it is parallelizable. But in Python, if you simply create multiple threads, that won't work. That's not true parallelization because of a global interpreter lock, meaning that in your interpreter, only one thread will be executing at a time, which will prevent any optimization. And in fact, it will slow it down due to overhead. The way multiprocessing in Python actually works is several interpreters need to be initialized, each having its own global interpreter lock, each working on its own CPU. But for them to communicate, there needs to be serialization of your data. So you can think of it as like you need to pickle all the data, pass it around between different interpreters. And of course, that will incur overhead. So, for example, if you have 4 CPUs, that's one of the reasons why you won't observe 4x speed up exactly. Thankfully, that is abstracted away by joblib, which allows you to multi-process in essentially one line. You just need to define the parallel class. You specify the number of CPUs you want to use. So here I'm using all the CPUs that are available, and we have 16, I believe, on the machine that it runs on. Delayed is simply the way to not run the algorithm straight away. It serializes it and then executes it on separate interpreters. And as I said, so the parallelization in the algorithm that I outlined happens in batches of investors, or in fact, the scoring function also has a bunch of parameters, and you can also parallelize that. And that is what is called embarrassingly parallel, meaning that it's very straightforward to parallelize it because everything is independent of another process. All right, so usually that should be enough. NumPy plus parallelization. But if you want to work the last mile, if you want to squeeze that extra bit out of Python, you can use Numba, which is a very recent library. We prefer it to Python because it keeps the code base Pythonic. It is very easy to implement. It comes with quite extensive functionality for speeding up scientific computation, including parallelization. And in fact, as I will show earlier, it releases a GIL as well. And surprisingly, for the little amount of effort, as we will see, that it requires, it can actually be faster than Python, and it can match C++ code from what the open source community has demonstrated. Here's how it works behind the scenes. There's a lot of heavy loading. So as you know, the CPython compiles your Python function into bytecode. Then Numba analyzes that, creates an intermediate representation that is a template. Then it does type inference for you, rewrites that intermediate representation, and then passes on to LLVM, which is a language agnostic compiler that will perform further optimizations and rewrite that code into machine code for appropriate platform, either a CPU or it can even do GPU code for you. Let's see how it works. Here's a simple function to calculate return of the portfolio. So we define it simply as a weighted average of assets in that portfolio. It's very easy to vectorize. But as you can see in Numba, it will be 4 times faster if you provide it with the correct specs, so to say. So let's walk through the functionality and how, let's say, some performance tips for Numba. First, I have the decorator here, chit, which is the just-in-time, meaning that you won't be creating any compiled code ahead of time. It will just pick it up when you actually call the function at execution time, and only then do all the inference, all the optimization, and compilation. The first argument is type signature. You don't have to do it. Usually, Numba can infer the right types for you. But for performance-critical algorithm, I prefer to write them down because sometimes type inference might not work exactly the way you expect it to, integers being converted to floats and so on. Second parameter is the no Python mode. So when Numba cannot infer the types that it can work with, or when the type check fails against the type signature that you provide, it will fail to object mode, which is, you can think of it as just the Python mode. Any optimization gains will be essentially eliminated, and the code might essentially be slower due to overhead. Second one is a parallelization, so you can tell Numba to create multiple threads and release the global interpreter lock. So this will be even faster than multiprocessing in Python because you are not serializing data. You don't need to communicate between several worker processes. It's true multi-threading. Yeah, but mind the overhead. You're still setting up threads. So for arrays of smaller than 100, I found that it's not worth it and it actually slows down the algorithm. But let's say if you have arrays of 1,000 or more, you will see significant speedups. The last parameter, the fast math, is what you're telling the LLVM compiler to auto-vectorize, meaning that the CPU will execute several operations at once, vectorization. But you need to be mindful of the fact that floating point arithmetic is not associative, so it will start moving around different numbers. And so you might get different results if you care about floating point accuracy. So if the 16th digit after the decimal is what you care about, then don't set it to true. And then, it's a compiler, so there will be costs of compilation incurred when you first call it. You can cache the results in memory or on disk, so that only the first time is slow, but all the subsequent times will be really fast. But don't JIT closures, so it's probably an interesting trick interview question. If you JIT a closure, does it compile every time you call a function or just once? It will compile every time you call the function, because the closure inside the function is defined every time you run that function. So that will be really slow. Some more tips from our experience. The type inference, as I said, may not always work as you expect, or Numba can fail to infer them correctly. So to be safe, pass type signatures. You know exactly what kind of behavior you'll get on the other end. You can pass multiple signatures, going from most specific to least specific, so 64-bit floats all the way to 8-bit integers. And it does compile code into something low level, so the exceptions that you may get can be very obscure. So some debugging tips: you can access the intermediate representation by calling the inspect types method on the compiled function, and it will essentially show you line by line how Numba interpreted that. I won't be showing you the output of that because it's pretty, well, it's not pretty, but what you need to look out for is the type. So it will, here from the previous slide, I had like float 64. So you need to look out that every argument that went in actually actually managed to infer coerce it into float 64. If it couldn't, what you will see is Py object, which means it will revert to Python mode. Of course, if you set the no Python argument to true, it will warn you. It will just throw you an exception, so it won't work. And finally, the annotate HTML is what will allow you to produce reports that will, again, show the intermediate representation with how Numba translated your code. Even though the just-in-time compiler is sort of its core functionality, it comes with a lot of bells and whistles. It can do universal functions for you. So one of the workshops yesterday touched on that, Numpy ufuncs, that will do all the broadcasting for you, type coercion, and so on. You can even do generalized universal functions. So you can define your own broadcasting rules. Yeah. So this is a way to speed up convolution, for example. You can write CUDA compile code, and you can also, what they're still working on is like ahead of time compilation, so that you can compile ahead of time and then communicate with a remote service, for example. So here's our algorithm at a bird's eye view, bit of self-irony. As I said, three key components of the greedy algorithm: the filtering function, the scoring function, and then the solution function. The scoring function is the crux of it, and it's what takes the most time. So that's what we compile using Numba. The loop that the greedy algorithm relies on is inherently serial. So what goes next depends on what happened before. So you cannot parallelize that. So it's an inherently serial procedure. That's why Numba shines, because loops in Python are very slow. I'm sure many of you know that. And that's what Numba will make very fast. So our solution processes 1 million assets in 20 seconds, as opposed to days. It has so far processed tens of millions of pounds for thousands of investors, and never violated our key constraints. I do hope it made them as happy as those faces. And finally, some takeaways: simplify whenever possible, and especially when the problem is NP hard. Optimize for research speed first. That's why I think we use Python. It's so good for that. Profile before refactoring, and then delve under how things work under the hood to speed it up. And yeah, we've been very happy with using Numba. It keeps the code base Pythonic, easy to read, easy to implement, and people are discussing of replacing Python in some of the key PyData libraries, such as SciPy and pandas, for Python to Numba. So it has a lot of potential. Finally, if you want to learn more, you can go to our blog. And of course, as no data scientist is an island, so it's a lot of teamwork. And I would like to give acknowledgments to my colleagues, Kishan, Francisco, and Jihan. I hope you enjoyed the talk. Thank you.